Assalamualaikum and good morning.
Salam, good morning, Doctor.
Okay, so hopefully you have logged into your Putra Blast and downloaded the instruction for your mini project, which is a group project. Okay, so you can see on the screen the instructions for this mini project. Let's go over this first before we continue our class. Okay, so the purpose for this presentation is actually to see whether or not you are able to explain and elaborate heat transfer concept, okay, which you have learned. So it's more in terms of the ability to explain, and that explanation comes from your own understanding, okay? So that's the most important part. And that includes your ability to answer questions from me using your own understanding, using your own words. Okay, so that is part of the evaluation as mentioned towards the end of the instruction. Okay, and in order to explain the heat transfer concepts, you need to basically in your group study and prepare about the heat transfer applications involving these two aspects. Okay, the first one is daily life. So daily life is basically anything. It doesn't have to be related to technology. Basically anything that you do in daily basis or anything that you see every day in your surrounding, for example. Okay, but when you explain, you want to relate to the heat transfer concepts and be able to elaborate how that daily life application is related to what you have learned. And number one, so that's number one. Number two is you have to pick one application that is related to industries relevant to your field, which is mechanical engineering. Okay. And then in that application, choose one topic or one equipment or one scenario, anything that you can relate to heat transfer concepts and be able to explain them. Okay. If you have any questions, stop me and ask your questions. Okay, make sure you are clear about what are required from this for this assignment. Okay, so now the whole idea is to have a live presentation face to face. Normally I have this recorded, but then I thought this time it would be nice to have a real presentation. That's how I can better assess the students whether you understand what you're learning. Okay, be able to elaborate the concepts. So you're going to basically read and think through about what you learn, relate to the applications, and then prepare a presentation slide in your group, right? And then during the presentation session, you're going to present what you have, and then be ready to answer some questions that I have. So I plan to ask at least one question for each student. Okay, so all of you will be answering my question at least once. If I'm more interested or if I need to give you more opportunity, maybe I ask more questions, depends. Okay, but be prepared to answer questions. And then in your slide, you need to have a graphical visualization of your application. Okay, these two. And then explain the concept and the process. And you need to have a certain way to be able to elaborate the technical details and calculation related to that application. So for example, you can choose a case study. Okay, case study, a scenario or condition, a situation related to those applications, and then share about the technical details. So when you share, you don't want to like go through the steps like equations one by one. I'm looking for something more like how do I say, like an intellectual discussion where you talk about the theory and how it relates to the concept using what equation, but not like saying or spelling out the terms one by one. Okay. Do you understand what I mean? So don't read me the equations. I mean, we can look at the equations from your slide. It's quite obvious, right? But you have to explain what those equations are and like what you get from it, what you need from it, things like that. Okay? So that's what I'm looking for in this part where you need to talk about the technical details and calculation. So if let's say any group, any member of any group kind of explain it by translating the equation as a verbal equation, you know, like you're reading the equation, I'm going to stop you and ask you to explain in a better way, related to equation of course, but not like going through each term one by one, each operation one by one. That's not I'm looking for. Okay, so practice that. If you have any question, you can ask me. Okay, and then certain guideline, provide titles, full name, metric number, and then you need to upload your slide in Putra Blast. Okay, we'll talk about the deadline later. And then this is duration for your presentation, and then we have a Q&A session. Okay. So please be ready for your Q&A. I hope that I don't have to wait for a long time or, you know, asking you many times in order to wait for your answer, because otherwise we will not have enough time for all groups. And therefore, if that happen, I think I'm gonna need to pass. Okay, basically move on, and that person, that student who need more time to explain is basically might not be receiving good score. Okay, so the point is be ready from now, practice, discuss with your group members those concepts that we talked about in class previously, those things that I remind you that you need to understand, and you know how to differentiate between certain things, what they mean, what they physically mean, things like that. Okay. So basically just try to answer the questions. Don't just keep silent or waiting for more time, because we don't have much time. All right. Okay, then about the deadline, I was thinking that the deadline is next week Monday, because next week is the last week, week 14. And then if we were doing it on Wednesday, it's not going to be enough for all groups. So I was thinking Monday, but that means it's a week from today. It's quite a short time. So I actually, I told your class representative that it's possible to have a later deadline. Okay, postpone this to maybe Friday, for example, of week 14. But then you need to provide me that 2 hours, let's say on Friday or Thursday, up to you, that you guys are available and we can have this face-to-face presentation session for all groups. Okay, so have you guys discussed that? Do you have the answer for me? When do you think is the best time to do the presentation, or do you want to stick with Monday 27th June?
No answer yet, Doctor.
Okay, that's fine. I guess you guys can still discuss. Let me know, but this is Monday, and then Wednesday you have your test. I'm just hoping, okay, if you're going to tell me not during class, because seems like we don't have class until next Monday, right? Because Wednesday is exam. Then I'm just hoping that the information is actually representative of all students, okay? Meaning all students aware of that change in the deadline and agree and available to come and present. Okay, is it clear? If let's say we stick on Monday, the other assignment that you have, which is numerical method, is actually due Friday, right? That week. So you can actually focus on this assignment first. And then you have about 4 days for the other assignment. I know you have other assignments from other courses as well. Um, so it's really up to you when you want to do the presentation. But what I'm trying to say is that I try my best not to have a heavy assignment. This is, just looking at some examples of application in daily life and industries. You can find this information is heaps on the web. You can always find something. And most of the time, the equations is also there. The situations, the scenarios, the case studies are also there. You just need time to look at it, to search, to understand, to discuss, and then prepare your slide and be able to present. Okay, it's not like I ask you to design something new, or I ask you to deassemble something and then do the analysis on that real, something real in front of you, and then bring that stuff in front of me during the presentation and show me directly which components you're talking about, like a physical system. That there's no such thing. Okay, this is a lot having to do with reading and then relate to what you have learned and be able to explain it again by doing the presentation. Okay, so first of all, understand what is required. It's not that much. So if you have motivation, positive attitude, you should be able to do this. Okay, I don't see Monday 27 as a problem, but I don't know your schedule. Let's say it's a very hectic week, then discuss among you to have a later deadline. Let me know, okay? In terms of the group, you can choose your own groups. So there's 25 students in this group, right? So 7 of you will have 3 members. 7 groups. And then 2 group will have 2 members. So that will be 21 plus 4, 25. Okay, so members, you choose yourself, discuss among you. So I hope that way it's easier for you to do the assignment, okay? So it's only one submission for the slide, one submission for each group. And I just need to remind you that it happened, I think every semester happened that one group at least, I don't know why, but there was always a case that a group did not submit. So, for example, there's 3 students in the group. None of them submitted the document. So it's a 0 for that part, right? So if you are not sure whether your friend submitted the document or not, why don't you just submit? If I got more than one submission, that's fine. I can easily keep track, or I have seen this document, it's the same one. Then I check my list, or it's actually the same group. So that's fine, okay? It's better than not having anyone submitted for that instruction than receiving 0 for the whole team. And then this is how you're going to be evaluated. So part 1, the first item here, this is focusing on solely how you explain, how you present, basically the delivery of the message. It's not on the message itself, it's on your presentation techniques and skills. So I'm looking at, you know, those energy in your presentation, those patient, eye contact, focus, things like that. Okay. So make sure your voice is loud enough, and then you're trying to make eye contact with your audience, because these are very important. Okay. And then part 2 is on the technical accuracy and completeness. So there's two parts. One is technical accuracy, means whatever you're saying is accurate. And part 2 is that whatever you're saying is complete enough for that situation, for the analysis. Doesn't mean you're talking about the equations one by one, but you're trying to explain it the best you can, covering all the important parts. Okay. And then 3, ability to answer questions, like I said. Okay, so these questions, it could be anything based on what I have taught you the last, what, 12 weeks, 13 weeks. Okay. And then 4 is teamwork. So teamwork is basically, I will assess teamwork based on how you present. So make sure everyone present in during the presentation session. But during Q&A, you cannot have a teamwork. So if I ask that question to student A, then student A needs to answer without student B and C giving the answer. Okay, so it's like 1-to-1 Q&A. But let's say one of your team member is not available during the presentation, then that could mean something. Okay, you should have a good discussion, good communication. If one student has a problem, try to solve the problem together, you know, as a team, and be able to present, you know, together as a team. So I made a point down there at the end that if you have same applications between at least two groups, I will deduct some points. Okay, that is just to encourage you not to have the same applications for your group and your friends group. Okay. I believe it's easy for you to discuss that, like you could have discussion in your WhatsApp group about what your group is going to get, so you can do first come first serve, things like that. Okay. Any question related to this assignment?
Actually, I have two questions. So the first one is regarding the graphical visualization. So we just like add pictures of how the concept works, right?
Right.
Is that it? Okay. And then my second question is, here only mentioned presentation, submission of presentation slide. So we don't need to do any report, right? Just only slide.
Right, no report. Okay, because you already have that numerical method assignment, so there's no report. So even your evaluation, there's nothing to do with report. That's why I said it's actually doable to have a week from today. You know, it's not that much actually. I focus a lot on your. Actually, what I'm gonna be looking at a lot is how you are able to present, to basically talk about the concepts that you have learned from your own understanding, from your own knowledge that you get it from this class. And that has to, you know, when you really appreciate a knowledge, right, you are able to talk about it in a passionate way, like you appreciate what you learn and you're trying to tell others about what you understand, um, sharing the knowledge basically, right? So that's what's important from this assignment. Even if you know a lot, but the way you present is not by your own words, maybe you're reading notes, for example, or you're reading your slides, then it's a bit an issue there. Okay. But of course, part of it is also on the accuracy and completeness. That means, you know, if you're passionate enough, you try to understand what you're talking about, right? So that you can share with others. Okay, about the graphical visualization, um, you can have a picture, you could have a video, but when it's a video, please, number one, not to have a long video because otherwise you run out of time. Number two, I don't want explanation from YouTube, for example, or other people's doing the explanation. You can have the video, but you need to explain it yourself from your own words. Okay, I don't want you to memorize whatever that video is saying because I could easily differentiate between your own words, your own understanding, and something that is a result of memorization. So don't do that. Okay, don't memorize. That's not the whole point. Okay, any other question? Okay.
Okay.
Yeah.
About the presentation, everyone is agreed to do the presentation on Monday 27th.
Oh, okay. So you're going to do it on Monday 27, right? Did I hear that correctly?
Yeah.
Okay, so we're going to stick with this. Okay, what I can do for you, if it's helping you, all of you, I can postpone the numerical method assignment on to be due on week 15, for example, if that is better for you. Because that is only submission through Putra Plus. We don't need to have a face-to-face session for that, right? So if that's something helpful, we can do that. Let me know, okay? Sharon, you let me know about that after you discuss with your friends. So that is another way I try to help you, giving you more time for the other assignment. Otherwise, we can stick with, I think it's originally Friday, same week, 1st July, I think, 1st July for the other assignment. Yep, 1st July, could be 5 p.m. I think. If you need more time, it's okay. I can give it to you, but we have to make it officially like when is the new deadline. Let me know and we do that, okay? But for the presentation, I think that's a better choice. We stick with Monday 27. Even if I need extra time to explain on heat exchanger, we can do it online, maybe at night or something. Okay, but we can reserve this 2 hours Monday on next week for the presentation. Okay, thank you for that. Any concern? Anything else? Okay. If no question, let's continue with you were in chapter 8, which is internal flow. Okay. We actually almost done. Now I'm going just to end a little bit and then continue with the next chapter, which is related to this earlier part of the discussion. Okay, so in internal flow, you learn that you have two cases, right, of such internal flow. One is when you have constant heat flux. Oh, by the way, I have shared with you the videos in the Google Drive. Okay, please have a look if you need to review some of those. And then the second one is constant surface temperature, right? So basically the way you treat the temperature is different for these two different cases. And then from the second case, you have seen equation that the natural log delta T out equals negative the parameter length H bar. Okay, so you have seen this before. This is basically after we integrate the differential equation for that differential element in internal flow. Remember, we talk about that, and then we arrive at this equation. So from here, we can actually say the term m dot cp is basically just rearrange, right? Okay, and remember delta T is T surface minus T of the fluid, the mean temperature of the fluid. So this is for internal flow, internal flow. And if we go back to the other definition of Q, which is it's not the other, it's actually the same one, m dot Cp. In general, the heat transfer rate can be written as this, right, from thermodynamics. So this has to be multiplied by the temperature difference of the fluid. So this is outlet, inlet, right? This is from thermodynamics. It's actually coming from m dot delta H, and delta H is represented by the relationship between Cp and delta T. Okay, thermodynamics, if you remember that. And then we're going to rewrite this using that delta T, okay? Because what you have there is Tm, which is this second term in delta T. So that is equivalent to saying that I have Ts minus Tm inlet. Okay, I have that minus Tm inlet, so minus Tm inlet. And then minus, so notice that I introduced Ts. So I need to get rid of Ts because there is no Ts in there, right? So now I minus Ts, so Ts cancel, and that's fine, that's good. But I need this term, Tm out, right? So in order to have that, I'm going to have a bracket here, and this is positive, so it's minus, 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 becoming a positive Tm out. So we recover the original equation. However, now we can write the equation in terms of delta T, which is defined by this, right? So we have m dot Cp, this is delta T I, right, for the inlet, minus this is delta T for the outlet, so delta T out. Okay. And here we have a relation between m dot Cp and the other terms, okay, from this analysis, right? So we can further replace that term here. So I'm just going to write down that is actually this term, and then multiplied by that delta T difference. Okay. Okay, so if we compare this equation now, this Q, in terms of the other Q that we know, which is H times the area, surface area times delta T, right? You have seen this equation even from chapter 1, the first chapter. I think that's chapter 2. Okay. You have the H, right? So here H, this is also H. Area, this is area. Okay. So then the rest of it is actually delta T. So this term is delta T, right? If we compare with the other Q. So it means we can rewrite this equation, Q equals to H, okay, area. So area in this case is the perimeter times the length, okay, times what is called as the delta T log mean temperature difference, okay, log mean temperature difference. I believe you have heard this term before in your one of the labs that you have previously. Okay, so log mean temperature difference is basically temperature difference that represent it's a term that represents temperature difference relevant to internal flow when you have a constant surface temperature case, okay, whereby it is given by, so where delta T log mean is basically all the terms in the green box, right? Notice you have a negative there, so I'm going to write down the delta T out first because of this negative. It become positive, right? Delta Ti divided by natural log delta T out over. Okay, so this is where log mean temperature difference was basically developed, where it came from. Okay, so this term is called log mean temperature difference, and it came from the derivation of constant surface temperature. You remember the derivation? So if you don't remember, you can look at the previous videos. So we derive this equation until you get that equation, and then today what I did was to use this Q and using the m dot Cp from the other equation put together, and then using the Q that is related to convection, HA delta T, and therefore from there we get this log mean temperature difference. So you could do something like this if the question asks you to derive log mean temperature difference, okay? And this is actually related to heat exchanger. You're going to use this LMTD again in heat exchanger. We'll see that soon today. Actually, there's a third case, okay? This is 1, 2, there's a third case. Let me talk about that. This is when you have a constant T infinity, okay? Which is the temperature of the surrounding. So this is the case when you have your internal flow, okay, your pipe. So that's a fluid going in with a certain mass flow rate, convection coefficient, right? And then this has a length. So the fluid comes in with inlet temperature, leave at outlet temperature, and the surrounding is actually like an external flow, okay? So this is a case where you have internal flow together with external flow. So this is internal, this is external, right? So the outer flow becomes external and it comes with T infinity and HO, which is the convection coefficient for that surrounding or outer flow. Okay. So what happened in this case, we can use similar equation here. It's just that instead of having H, okay, instead of having H in this equation, we're going to replace that by U. U is like the heat transfer coefficient, okay, that represent how fast, how good the heat transfer is going on from the hot to coldest fluids, okay, but it considers all the mechanisms that are involved at the same time. So in other words, U is going to represent external plus internal for this case number 3, because you have external and internal, right? So that's why they don't use H, they use it they use U for that purpose. Okay, so H becomes U. You'll see that in heat exchanger, and then when we have this delta T, okay, which is Ts minus Tm, in the third case, delta T is going to be, the Ts is going to approach the T infinity, right? Because your surface is now exposed to the surrounding outer fluid at T infinity that is constant. So the temperature is kept constant. It's not like it's not reducing in terms of the heat. It's constant temperature of the surrounding, which the surface of the internal flow, the pipe, will eventually trying to be in equilibrium with that constant T infinity. And that's why T surface is approaching T infinity. Okay, so delta T, not the log mean temperature difference, but this delta T. Okay, this delta T is then T surrounding minus Tm. Okay, for this third case. Remember that for the second case, delta T is Ts minus Tm. Now this is approaching T infinity. So this is what you have for every term that you have delta T. Okay, in order to get the delta T log mean. So the way we actually represent this situation is basically we can use the thermal circuit representing external flow. So you have a circuit resistance for the external flow. Okay, so what is the R resistance? That will be 1 over H out, right? This H out, and then it is actually in series, right? This is external, and then there is this conduction. Okay, conduction across that thickness of the pipe. So that is 1 over K. K is the conductivity of that material that construct the pipe. And then you have that internal flow. So it's a series combination of different mechanism. Okay. And so the U is basically all of this combined. Okay. So let's look at chapter 11, heat exchanger, because it is the continuation of this. Okay. You'll see that chapter 11, heat exchanger. So heat exchanger is heat exchanger. Sometimes it's just HX, okay? Okay, so heat exchanger is a device that basically exchanges heat between two fluids, right? And there are different types of heat exchanger. You can read about it. There's concentric tube, shell and tube, compact heat exchanger. Okay, so from time to time, people design better heat exchanger, more compact, for example, lightweight. For example, they talk about reducing the cost while increasing the effectiveness, the efficiency. Okay, so there's a lot of improvement, but we're going to look at the basic heat exchanger. Okay, because if you understand the concept from this basic design, you can actually apply and extend to more complicated designs. Okay. So we're going to consider concentric or what's called as tube heat exchanger. Okay, which is basically you have one tube in the middle, and then there's another tube. Okay, enclosing that inner tube. So then you have one fluid going in the inner tube, and another fluid could be hotter or colder going in the other region. And then while they flow, they actually exchange heat, right? So let's say this is hot. I'm just giving an example here. So let's say this is the cold fluid, so it flows in, and then you have a hotter fluid flows in. So while they flow inside the tube, it will actually exchange the heat. So you could expect the temperature of the cold fluid at the, so let's call this inlet and let's call this outlet. Okay. So the cold fluid at the outlet will be greater than the cold fluid at the inlet, of course, right? Because it's going to gain heat from the hot fluid. And then the hot fluid is the opposite. The hot fluid at the outer will be less than hot fluid at the inlet. Okay, so that's the general idea. And then if you look at the setup here, in terms of what's going on related to the heat transfer mechanism, it's actually a lot having to do with case 3. It's just that the other mechanism, so you have inner or internal flow there, and you have another, and then you have conduction across that thickness of the tube, okay, and then you have another convection going on here, right, on the other region of the tube. And the conduction across the solid here, this actually depends a lot on the thickness of the tube. If it's very thin, okay, very thin tube, then might as well you don't have conduction. I mean, it's not that it does not occurring, but it is not significant compared to the convection that's going on, okay? So that is normally for a thin pipe. You could also have other things going on the surface of the internal tube, right? Let me use in color. You know, as the fluid flowing in over time, it can have what we call as the falling. Falling is basically sedimentation, okay, on the surface of the pipe. You could also have falling on the inner surface. Okay, so this is like another layer of conduction. Okay, it's like a new thickness that is composed of most of the time is the minerals. Okay, if you have water or brine that flows in, we know that water has minerals, is very fine particles, but as it goes like a long time, it actually deposits on the surface, and eventually from time to time, after a long time, we'll start to see that thickness of the sedimentation of the particles, right? And it becomes like another conduction. So overall, we can write what's going on in terms of heat transfer as the combination of all this. Okay, so let's do that. First, okay, now we focus on this heat exchanger. Okay, this is our domain. Okay, the heat exchanger. So the first thing is the convection on the outer region. So that will be 1 over H. Okay, so I'll call this HI. Sorry. I'll start with, this is HO. Okay, I'll start with this the inner tube. Okay, HI times the area. Okay, if you need to have a Q, you need the area. So this is we're talking about the internal flow of that internal tube. So it's HIAI. Okay, and then let's say there's falling, the green deposits, right? So you're going to have that falling. So falling is represented by the falling resistance. Okay, and this is for the inner tube, the green color. Okay, and then you divide by the area. So what is this? This is basically much like for convection you have 1 over H. For falling is what is called as the falling resistance. Okay, and the value you can get it from table. This table in your book, in textbook, I don't remember the table. Okay, You can Google Fouling factor table. If you have textbook, this is table 11.1, or maybe later I can give it to you. Okay, so it's basically a certain value depending on what material, if I'm not mistaken. Okay, or what fluid, something. Remind me to share it with you. Okay, and then plus, then after falling, you have that conduction across the solid of the tube, right? Okay, so if we have a cylindrical pipe, most of the time we have cylindrical, right? Then we're going to use cylindrical wall equation, which is given by this. So this is actually for the conduction, okay? Conduction across the thickness. So this is conduction, okay, of that solid, okay? Not the fluid, it's the solid conduction. This is length. So this has the K, right? Whatever that material is. Length is the length of L is the length of the pipe. D O is the outer diameter of the inner tube. So if I draw the inner tube, this one, you actually have something like this, right? This is kind of exaggerated a little bit. So this is a thickness. This is DI, okay, and then this is D out. Okay, so then the ratio, the natural log here is actually giving you kind of like the thickness of that inner tube. Okay, this shaded region. But it looks a bit weird because it's cylindrical coordinate, cylindrical wall. Okay, and then you have that if you have falling on the outer surface of the inner tube, which is this green color. So this is sedimentation or falling due to the other fluid, due to the fluid flowing through that outer region. Okay, so that will be much like the other falling. So that will be falling for that outer space divided by the area. Okay, and then plus you have convection for the other region, which is 1 over HOAO. Okay, so all of this is actually going to be equal to what we call as the efficiency. Okay, efficiency, the performance, efficiency of performance of the heat exchanger. What we call as the U. Okay, this one. This is like the overall efficiency, okay, because you have conduction, convection, even you have two convection, and you could have falling. So this is equal to 1 over the efficiency. And because you're talking about Q, we divide by area, then you have area also on the left hand side. Okay. So U is like overall, it's called the overall heat transfer coefficient. It's much like H, which is a heat transfer convection coefficient, but U is more like overall because it combines convection, conduction. You could have more than one convection, right? More than one conduction. So overall is called U. Okay, so if the question, if you need to know what is the overall heat transfer coefficient for your heat exchanger, if you have a concentric tube, then this is the equation. Okay, if you don't have falling, let's say it's a new equipment, then you don't have that term. That is only for falling. Meaning you have the heat exchanger has been operating for quite several years. that it starts to develop that sedimentation inside it. Okay, otherwise you don't have to bother about it. Okay, any questions so far? Um, Later, which is Wednesday next week. Um, Actually, I will look at the class replacement. Do if we have had enough class replacement, because I remember we have quite a few, several classes that we miss. So let's say we still need more replacement, um, which I may need in order to cover the remaining part of chapter 11. So we're going to arrange for that class replacement online. Hopefully I could cover the next topics in this chapter. Okay, because you need to learn how to determine the performance of heat exchanger. So there are two approaches. Okay, you will learn that later. Okay, for now, we do example related to what we have talked about just now. Okay, so I'll give you a question and also take a break, 5 minutes, and then we discuss and look at the example. Okay. Okay, let's continue. You see the question, right? Okay, let's look at the question. The condenser of a steam power plant contains, okay, so this is a bit different because you have a number of tubes, okay, 1,000 tubes. So you need to understand what that means. So each tube has inner and outer diameter given, okay. And then steam condensation on the outer surface is characterized by convection. Okay, so HO is given, right? So if we draw one tube. If we draw one tube, so I'm just going to draw like the cross sectional, right? So you have inner, and then the tube, right? And then the outer fluid. Okay, so this H out is given 10,000. Okay, and there are 1,000 of these tubes. Okay, so N is 1,000. And the tube K is given. Okay, so K of the tube is given. DI, okay, DI is basically this one. Okay, DI is 25 mm. Okay, and the outer tube, so outer diameters. Okay, outer diameters, that will be 28. So you can tell the thickness of that tube, right? So A, if cooling water from a large lake is pumped through the condenser tube. So this is the condenser tube, okay. There is a cooling water, okay, pump at m dot equals to. So this is the rate of the cooling water. So C is for the cold fluid, which is a cooling water, 400 kilogram per second. What is the overall heat transfer coefficient U? So find U based on, okay, look at the sentence. What is the U, overall heat transfer coefficient, based on the outer surface area of the tube? Okay, and you're given the properties of water. You have mu, and then K and Prandtl number. Okay, so find U based on what is it? Outer surface area of the tube, meaning you want to get it based on A outer, okay, AO. Okay, what does that mean? When we have this equation, okay, you notice that the left term is U that you want, the overheat transfer coefficient, and then it's multiplied by A. So a question is, what is this A? Is it AI or AO? A inner or A outer, right? Because you have two kinds of two kinds of area, AI and A outer. So which one? So when the question says explicitly mentioned that the U is based on outer surface area, outer surface area of the tube, okay, it means that equation is actually 1 over U A outer. Okay, the rest is actually the same as this equation. And what it means is that you want the U. So later on, you need to write it as, okay, in this case, we don't have falling for the first part A. I think part B is talking about falling. So part A, no falling. Then what we have is only the convection and conduction. So let me write it first. That will be 1 over HIAI plus natural log okay plus 1 over HOAO, right? So without falling, yeah, only these terms. Now you want to solve for U, right? Overall heat transfer coefficient. So what you're doing is remove the area. That's why you need to know whether this is based on outer or inner surface area. Okay, so then we're going to move it to the other side. Then it's A naught over HAAI, A naught natural log. So all the terms, but now multiplied by A outer. Okay. So if the question asks U based on inner diameter or inner surface area, so it's the other way. You do 1 over U A inner. If the question doesn't say anything, it's just saying find the overall heat transfer coefficient. So you have the freedom to choose. Your analysis is based on which area, okay? But you have to mention that in your solution, okay? It's like you choose one and then you proceed with that condition, okay? Is it clear? Okay, so something can cancel. And then area is pi dl, right? Remember convection is pi dl, parameter times the length, right? A outer is actually pi d outer times length. This is pi d inner times length. The reason is because we're going to cancel certain things. What is this? Pi the outer length, natural log pi KL. So pi cancel, L cancel, and then this one is 1 over H outer. So what you have is d outer over HI DI plus d outer the natural log 2K. This is the thickness conductivity or the tube conductivity. Okay, so this is 1 over U, but you want U. So later on, after you get all the terms, U is basically 1 over the whole thing, this whole thing, right? Then you get the U. So D outer, D inner is all given, conductivity is given. So H out is given, that's nice. You need to get H inner, H of the inner tube. It's not given, right? In the question, it's not given. So this is then related to chapter 8 because you need to get the heat transfer coefficient, convection of the inner tube. So it's internal flow. We're talking about this, if I make it 3D, this internal flow, right? So how do you get H? HI? Now I need to ask question. How do you get HI? Someone?
Using Nusselt number.
Right, thank you. Very good. Okay. So always remember, use Nusselt number. This is internal flow. So Nusselt number for internal flow. So it's H D over K, right? So then H is the Nusselt number times the K divided by the diameter. Now this is talking about the inner tube. So it is DI, the inner diameter, okay, of the tube. So you need to get K is then the conductivity of the inner fluid, which is water, and K is given, right? So that's nice. So get Nusselt number. Okay, so to get Nusselt number, what do you need? So this is a review. To get Nusselt number, what do you do first?
Find Reynolds number.
Right, very good. Okay, find the Reynolds number. So for internal fluid, remember that Reynolds number is 4m dot over pi d mu. So this is for the water. Mu is given, d is di, m dot. What do you think about the m dot? What is m dot in this case? Okay, think about it carefully. You have cooling water from a large lake is pumped, okay, is pumped to flow through these tubes, and there are 1,000 tubes of such diameter. Okay, so it's like you have another tube. So this is only like this tube is only one tube, but there are a total of 1,000, and the whole water is actually flowing through that 1,000 tubes. So what is that? How does it affecting your calculation in terms of that 1,000? What do you think? What happened to m dot? M dot cooling water. Class?
Do you multiply it by 1,000?
Okay, that's a good try. Okay, the way to think about it, okay, is like this. You have heat exchanger. So I'm going to draw it from the sides now. So you have heat exchanger, and then you have 1,000 tubes, okay, and this exchanger is connected to, basically, of course, you have a piping system and it's connected to the pump, right? So somewhere there's a pump that pumps the cooling water from that large lake to the heat exchanger, right? So now the cooling water is approaching the heat exchanger at m dot equals to 400 kilogram per second. So now when we analyze like this, we are actually looking at only one tube, right? Basically, the rest of the tubes are the same with the same diameter, same di, do, same length, right? The only difference is that you have 1,000 of them. Okay. So then this fluid, which is coming at m dot 400, is now like flowing everywhere inside that 1,000 heat exchanger tubes. Heat exchanger with 1,000 tubes. Okay, so each tube, what will be the m dot?
Divide by 1,000.
Right, you have to divide by 1,000. Okay, it's like you imagine like you have 400 something, right? And then it goes through 1,000 channel. So I mean, this goes through fast and this water is flowing. So it's most likely, logically, it will without any blockage or anything, they will have equal opportunity to flow inside that 1,000 tubes. Okay, so some of it goes to the first tube, then second tube, third tube, and so on. So they are actually equally divided. Okay, then each tube then will get 400 divided by 1,000. Okay, that is the net mass flow rate for one tube. And we do that because in our analysis, we consider one tube only in our equation, right? This is only equation for one tube, one inner, one thickness, and one outer flow. Okay, so that's how you do it. So that's how you get your m dot. So it'll be 0.4 kilogram per second. Plug in here, okay, and then plug in the I mu. You get your Reynolds number. Okay, that is in my solution is 21220. You guys please try. Okay, we don't have time, but try on your own. So if you have this Reynolds number, what kind of flow is this?
Lamina.
Is it laminar?
No, tubular.
But right. Do you remember what is the critical Reynolds number that divide laminar and turbulent for internal flow?
2,300.
Very good. Okay, very good. That's very good. You remember the critical number. Okay, now this number is a lot greater than that. So definitely the flow is turbulent. This is like 1 order magnitude higher than the critical Reynolds number. So it's turbulent. So you look at the correlation for chapter 8, correlation for internal turbulent. Okay, I believe I have shared that with you. Can you double check? Okay, look at the correlation. So you see, it's nice because this chapter is also related to other chapters, which is chapter 8 in this case. Let me see. I think I've shared to Shahrin. Yep, okay. So you have turbulent, right? You're looking at the Nusselt number. Okay, so which expression are you going to use? You have a number of turbulent correlation. 1, 2, 3. 3. Okay, and then there's Prandtl number range. So your Prandtl number is, what is the Prandtl number given? Prandtl number 6.6, isn't it? 6.6. Okay. And then Reynolds number ratio range is also given. Okay, L over D. L over D. The ratio between the length and the diameter. Let's check that. What is our L over D? But I think everything is L over D greater than 10, isn't it? Hopefully you guys looking at the table because that's what I'm doing now. L over D greater than 10 is actually for all correlation, so it doesn't make any difference. Okay. So if the situation shows that you can use any of the correlation, that means you can do that. Okay. 6.6. Yep. Greater number 5, 10 to the 6. Okay. I think all the correlation can be used. Okay, which means that if we look at the equation, I would say the first one is the easiest, right? Because otherwise, the second one you need that ratio of mu, and then the third one you need to have the f. So let's stick with the easiest one. Are you guys following me? So Nusselt number according table for turbulent is 0.023. Reynolds number, the power is 4/5. That one is 4/5. Prandtl number times n. Okay, and then what does it say about n? N equals to 0.4 for t surface greater than t infinity. And the opposite is n equals to 0.3. Okay, so let's check our TS and T, is it T infinity or TM? It's TM. Okay. So that determines the value of N. TS is, oh, where is it? Do we know temperature at all in the question? Okay. Temperature is not directly given, right? The reason is because you also are given the properties, so you don't need temperature. Otherwise, you need temperature to get properties, right? But what you know is you have cooling water that goes through the inner pipe, right? So this is cooling water, which means that the temperature will be less than the surface, right? So this is less. In that case, what is N? N equals to 0.4. Okay, so this is 0.4. So you plug in Prandtl's number, Reynolds number, Prandtl number, and you get the Nusselt number, which is I don't have it. Okay, you can calculate that. Then once you get Nusselt number, you plug in here, and the K and D, get the H, and H is in my solution is 3,400. Okay, there's a H. So that H is here. Okay, then you have everything in order to get 1/u and then inverse to get the u. So u is equal to the answer, u equals to 2255 watt per meter squared Kelvin. Okay, any question? Any question, class, on this? Okay, the second part, part B, after extended operation, falling provides resistance. So here R is already given. At the inner surface, what is the value of U? So basically, you just repeat all the terms are the same except that you have additional term in your equation, which is the resistance at the inner surface. So that is actually this one. This is not 0 for part B, and the value of this is given. Okay, this one is given, which is 10 to the negative 4. Okay, so you plug in that value, divide by the area, don't forget, and then you will get the new 1 over u and then the new u. So for part B, u equals to 1800. Okay, so you see that the heat transfer coefficient, the overall heat transfer coefficient, which is u, is reduced. Initially, it was 2255. This is for the case of without falling. It's a smooth surface without falling. 2255, and then over time, when there's falling of certain resistance, then the coefficient reduced to 1800. So that is why actually we don't like falling in heat exchanger. There are methods people come up with to get rid of this falling, to mitigate falling, basically to prevent it from happening. It still happens, but trying to reduce the thickness and so on. Okay. What is the time? We still have time. I thought I go to the next topic. Okay. Okay. So what you saw just now is how to get U, which is the overall heat transfer coefficient for concentric heat exchanger, concentric tube heat exchanger. Now, we want to determine what is the performance. Okay, performance. This is heat transfer coefficient, the overall. If you notice, in order to get the U, which is using this formula, right? This one. It's actually, this U is actually basically a combination of the different coefficient, HI. So HI is this, H out is this, the outer convection, and then conduction, right? And if we have falling, right? Sorry, I meant to say this one just now, and then falling, right? So it's actually just about the design of the heat exchanger, and then the flow itself, like talking about what is the m dot of the fluid, what is the properties, and then get the H, right? But if we have heat exchanger, we want to know the performance, efficiency, right? Performance. In general, we call it as performance of the heat exchanger. Then it's actually talking about what would be the outlet temperature of the cold fluid, how much heat is actually being gained from the hotter fluid, right? Things like that. Okay, talking more about Q and then about the outlet temperatures. So it's a bit different than the U. Sometimes we need U in order to get these quantities. Okay, so it's actually related. But what I'm trying to say is that if we analyze heat exchanger, just looking at U is not going to be enough, because we also need to look at other quantities like Q and the outlet temperatures. Okay, so in order to know the performance, there are two methods. The first one is called the log mean temperature difference method. So log mean temperature difference is a lot like the one you saw earlier for the internal flow. Where is it? This one here. Okay, it's something similar. Okay, but it's going to be specific for heat exchanger. And then the other method is called the effectiveness NTU method. Okay, so let's look at one by one. Log mean temperature difference method. Okay, so let's derive first. Consider you have concentric heat tube heat exchanger. So now what I'm going to draw is like concentric is like this, right? So what I'm going to draw is like half part of it. Okay, like this one. Okay, so imagine you have that inner tube and then you have that outer tube. Let's say this is m dot cold fluid coming at cold inlet temperature. So this is inlet. And then hot fluid is flowing on the other tube at a certain hot inlet temperature. And then it's leaving, right? The hot outlet. So this is outlet. The cold outlet. So you know that heat transfer is going to happen from the hot to cold fluid. Okay, and that Q, according to thermodynamics, Q is gonna be m dot C times delta T. Okay, so now we're going to write that for the hot fluid first. So this is m dot hot fluid, C for the hot fluid. Okay, this is CP, actually CP, but for the hot fluid. Delta T is the difference in temperature of that hot fluid. So it's T hot inlet minus T hot outlet. Right, because inlet is hotter for the hot fluid. Now, this is also similar to the other Q for the cold fluid, right? Because one is losing the heat, this one, the other one is receiving the heat. They are equal. Okay, so for the cold fluid is m dot cold fluid C for the cold fluid times delta T. Now delta T, it has to be T cold out first because that's hotter than the T cold inlet. Okay, make sense? All right. Okay, so sometimes you want to use this equation, sometimes this, sometimes you have to make it equal because of this relationship in order to get your unknown. Okay, for example, if the unknown asking for the T cold outlet, so it appear in here, T cold outlet, right? Which means you need to get the information on T cold inlet, M dot, C, and Q. Maybe you don't know Q, but you can get Q from the other Q here. So you need the M dot hot, C hot, T hot in, T hot out. So you get Q, then you can plug in here and solve for T cool out. So something like that. Okay. Any question? Right. So now that you know Q, U for the overall heat transfer coefficient, then we can write Q also in terms of overall heat transfer as being UA times delta T, right? This U is this similar U that you saw earlier. Okay, this U. Okay, this U. This U. So this U here with this equation is the U that you have when you analyze the heat exchanger. Okay. A here depends whether you are doing the analysis based on outer or inner surface area. This delta T is the log mean temperature difference delta T, okay? So that is given as let me write it first. Delta T2 minus delta T1 divided by natural log. Or you can do the other way. Also is fine. As long as you be consistent. Okay, this is also log mean temperature difference. Notice that if you have two first, you have two on top, one first, one on top. So what are these? What are these delta T1, delta T2? Okay, it's actually depends on your flow arrangement of the hot and cold fluid. In this first case, okay, you have what we call as the parallel flow. The hot and cold fluid are flowing in parallel direction, same direction. Okay, then what we mean by 1 and 2 is actually inlet is 1, 2 is outlet. Okay, so delta T inlet for parallel flow, okay, where the direction is similar for both fluids, delta T1 is the temperature difference at the inlet. Okay, so in that case, delta T1, this is 1 now, is T hot inlet minus T cold inlet. And delta T2, which is at the outlet, this is 2, is the temperature difference here. So delta T2 is T hot outlet minus T cold outlet. Okay, that's for parallel. Now let's look at what happens if you have a counterflow. So counterflow is the opposite direction. You have one going in one direction and the other one going in the other direction. Okay, this is counterflow. So 1 is inlet, 2 is outlet. So let's call this T cold inlet. Let me just be consistent with my notes to avoid mistake. Okay, so cold will come from the other side. This is hot. Okay, so this is T cold inlet, leaving at T cold outlet. This is T hot inlet, leaving at T hot outlet. So according to this arrangement, where you have a counter flow, delta T1 is this. So that will be T hot inlet minus T cold outlet. Number 2 is that. So that will be T hot outlet minus T cold inlet. It's actually different, okay? Different than the first arrangement. You can double check that. Because the first one here, you have inlet minus inlet, outlet minus outlet. The other one here is inlet minus outlet, okay? Outlet minus inlet. So it's different. This equation for the delta T, it will be different for different flow arrangement. But the overall formula for Q is the same, which is given by that expression. Okay, any question? Okay, let me just explain to you what happened to the temperature if you have a parallel flow. Let me use a new page. Okay, if you have parallel flow where the flow is going in the same direction, if we draw the temperature graph, right? This is 1 at the inlet and this is 2. T hot inlet is if this is temperature, right? And this is like the length of the pipe or heat exchanger, the tube. Okay, you have a hot temperature initially at the inlet, and then it's going to lose the heat, right, as it flows, because it lose the heat to the cold fluid, so it's going to lose some of the temperature, the heat, like that. Okay, until it gets to T hot outlet here. The the cold temperature comes in here, T cold inlet, and it gets hotter and becoming T cold outlet, which is hotter than inlet. So you can imagine that the coldest temperature is actually T cold inlet, right? So it's gonna be here, T cold inlet, and then it's going to get heated as it goes. The picture is not that good. So this reduce, it's going to gain the heat, right? Like that. Okay. So this is at 1, this is at outlet 2. So that's how the temperature looks like if you have a parallel flow. If you have counter flow, you have opposite direction. So if we draw the temperature, you have temperature hot coming in at inlet 1. So this is 1. So this is T hot inlet. Again, it's going to reduce the heat, right, and become T hot outlet at 2. So this is T hot outlet, but T cold outlet is going to exchange to get the heat from that T hot outlet. So this is T cold T cold inlet. Okay. Okay, that's T cold inlet. And then it's going to get heated until it is hotter and become T cold outlet. So what you have is a fluid that is lower in temperature at the outlet and then increasing in temperature. So this is T cold inlet. This is this one here is T cold outlet. Okay. And here this is T cold. It's T cold inlet, outlet, but it is located at that location 1. Okay, the reason we do 1 and 2 is because we don't want you to get confused between inlet and outlet. So inlet and outlet actually depends on the fluid. If, for example, the cold fluid, right? This is the cold fluid. It is entering at the end. Then this become the inlet for that T cold. Okay, not location 1. So 1 and 2 is not necessarily about inlet and outlet. It's about one fixed location. Okay, but the temperature of the fluid inlet and outlet depends on where on the heat exchanger that the fluid comes in and leaves. If it comes in at location 2, then location 2 become the inlet for that fluid, just like this T cold fluid. Okay. So then here at location 1 is actually the outlet for cold temperature. So it's T cold outlet. So this is how it looks like for counter flow. And you notice that if you have a counter flow, the outlet temperature of the cold fluid is going to be greater than the outlet temperature of the hot fluid. Okay. So T hot outlet is going to be less than T cold outlet. If this is the case, then what you have is a counter flow. Okay, I have exercise for that. I'm going to share with you after this. You guys please try. And then we discuss in the next class. So next class, it will be test, right, on Wednesday. I will communicate with Shahrin to see, I will check first if you need actually another replacement class. If yes, you need additional session to replace what we missed last time, then I will cover the solution for this other example on that during that class, okay? And then Monday, next week, we have the presentation, and then we have Wednesday for another class. I want to talk about the other method, which is the effectiveness NTU method. This one, right? And then you are basically done with this chapter and the course. Okay. Any question, class?
Hello, Doctor. Can slightly to explain what is going to be in the Wednesday test? Is going to be 2 questions and how the question should be look like. It will be same as test 1 or what?
Okay. I believe it will be 2 questions, just like 2 big questions, just like test 1. And then it covers transient conduction, and then convection, and then external convection. Okay, internal flow, that will be in final exam together with heat exchanger for the compulsory part, and then for the optional section is gonna be the previous chapters, conduction, thermocircuit, transient. Okay, basically everything you need to study for an exam, but the 2 chapters that you haven't been tested, which is internal flow and heat exchanger, that will be definitely compulsory in final exam. I think it could be more, it's not like the question is different, of course, right? But more or less the taste is the same as this one, the shape of it. How do I say? Do you understand? So it's much like test 1, but covering different chapters. But of course, what we ask will be different, right? In test 1, you have derivation. There could be no derivation in test 2. So there are differences, but I would say the level of complexity is the same. Okay, something like that. Any other question? Okay, thank you, class. All the best for your exam. If anything that I need to communicate, I will communicate through Sharon, and he will pass the information to you. All right. Thank you, class. Take care.
Thank
Okay,
you,
Doctor.
Doctor.